All right, everyone, we are into Unit 2, Force and Translational Dynamics. So congratulations, you've made it all the way through Unit 1, Kinematics and Vectors, and we're on to Forces. This is a very connected unit to Unit 1 in that it explains or provides a better understanding of why things are accelerating, all of the speeding up, slowing down, and changing direction we saw in Unit 1. We're going to go a layer deeper to look at what causes that to happen. And units 1, 2, and 3 all together, once we get to energy, work, and power, are all really interconnected in that way. So by the time we get to unit 3, we'll kind of draw a connection of like, here's motion, unit 1. Why do things change their motion and accelerate? Unit 2 is forces. And then unit 3 will look at what is the ultimate source of all of that and what allows for forces to happen. All right, but before we get there, we've got to get through unit number 2. So, essential question is what causes the motion of objects to change? Because we established what motion is in unit 1. We understand that things move, they change their position, and that's just a purely kinematics understanding. But once we got to acceleration, we saw that the motion of objects can change. They can speed up, slow down, they can change direction. And what causes that change is what we're going to be getting at now. Like, why do things accelerate? We kind of hinted at that here and there. In unit 1, we'd have some situations like, well, what is it that's causing this acceleration to happen? And the short answer is a force. And force is what causes the motion of objects to change. But we have a slightly more detailed physics description, although it's a very short one as well. And it turns out we don't need to really get more complicated with our definition of force. Once we get to AP Physics, it's a push or a pull. That's all it is. Anytime that any object or person in the universe experiences a push or a pull, that is a force. We'll get to some further descriptive types of forces and whatnot, but that's it. We'll go into detail on various kinds of pushes and pulls and how we see the pushes and pulls show up throughout different scenarios. Now, this is a vector. We'll get into some variables and specific types of forces pretty quickly here, but we'll put down a general variable for this. So F for forces, capital F with a vector sign above it because it is a vector. That's our variable for force. And then the units that we'll be using are newtons. Let's talk about types of forces because you might have already seen or come up with a list of forces. There are many. There's more than just the 7 that we're going to end up listing here. There's lots of types of forces like electricity, magnetism, electromagnetic force, or electric force, or nuclear force. There's all kinds of stuff that we're not going to take the time to look at in Unit 2, but we have a list of 7 of them that we're going to see come up in some form. A couple of them are pretty rare. Like there's a couple that we really won't see a whole lot of, but we're going to put them on this list just because they will see some amount of mention at some point or another. I guess I didn't specify right. Translational dynamics is just like motion connected to force because something that's dynamic is in motion and changing, right? Experiencing changes. And translational dynamics is the study of how things change as they move in translational motion. That just means like up, down, left, right. So translational is like going up and down, going left and right, all the kinds of motion we've seen. Dynamics being how does the motion of objects change due to forces. We're going to start with a very familiar one. This is gravity. So gravitational force, force of gravity, however you want to phrase that. So this is, of course, a pull from the Earth, or it could be something else. We know of gravity primarily because of the Earth. The moon has its own gravity. The sun has forces of gravity, right? So it could be a pull from the Earth or any object with a large mass attracts other objects, right? So that's the whole idea with gravity is that it's an attractive force. The Earth, of course, attracts all of us by pulling towards the surface so that we stay on the Earth. And even if we jump or fly or whatever, there's always that attractive force trying to pull us back down. And what it does is it attracts other objects with mass. If there were an object that somehow didn't have mass, now, of course, we assume that any given object we're dealing with has some amount of mass. It's pretty hard to get a massless object, but anything that has some amount of mass gets attracted. And this force is directed downwards. Or rather, we could say it's simply directed towards Earth's center, or the center of, the moon or whatever. There it is, gravity, right? We should all be familiar with the basics of what gravity is or does in terms of, yeah, it pulls us and every other object with mass towards the Earth. We talk about like a zone of influence. We'll get to either in class or in some more detailed descriptions on gravity. We can talk about like zone in which, like, if you go far away towards outer space, there's still some gravity, but it's not as strong as it is at the surface of the Earth. For our purposes, we tend to stick near the surface of the Earth. Let's look at a variable for force. Force of gravity specifically. Capital F, and we're going to use some subscripts. So G is the force of gravity from the Earth, Fg. Now, we don't want to mix up force with acceleration. Forces, as we've kind of already seen, they cause acceleration. They cause these changes in motion. We're going to see that more clearly with Newton's laws, but they're not the same thing. Force is not the same thing as acceleration. Force is a push or a pull that is experienced by an object from something else pushing or pulling on it that causes acceleration, which is a change in motion. Right? They're not a push or a pull is different from the rate at which an object speeds up or slows down because of that push or pull. Units are newtons. That's going to be true for all of our forces, and we have an equation for it. So on the surface of the Earth, we can calculate what is the force of gravity. And it turns out that force of gravity is exactly equal to the mass of an object. This could be the mass of a person, a desk, whatever it is that's being pulled. And then times, this should be familiar, 9.8 meters per second squared, the acceleration of gravity near Earth's surface. They also call this the gravitational field strength is another term for this we might see. And the idea of gravitational field is just there's a zone of influence around the Earth. It's not just at the surface that objects experience gravity. Once you go out far enough, the gravitational field and the force of gravity gets really, really weak far away from the Earth. But, there's varying gravitational field strength as you go miles and miles up into the air and the stratosphere, and you get less and less force of gravity. That's because 9.8 on the surface of the Earth gets smaller and smaller, and by the time you're far up way above the Earth, you get like 4 meters per second squared or something. You simply multiply that 9.8 or 10 times the mass. Because we're pretty much going to stick with the surface of the Earth. We're not going to do force problems in, the stratosphere. The mass of an object in kilograms, which we'll get more specifics on and remind ourselves of mass and definition for it and all that later on. The mass of an object in kilograms times the gravitational field strength, or the acceleration of gravity, 9.8 near the surface of the Earth, rounded to 10 because of AP. That gives us our force of gravity. One interesting thing to note with that is this does change the amount of force based on the object. The Earth does pull more on you than it does on your phone, right? Because you have more mass than your phone, and therefore the forces are different. So this equation does tell us the Earth pulls with varying amounts of strength, with varying amounts of force on different masses of objects. But if you've ever seen the bowling ball feather video, which we may watch at some point in class, you might think, oh, the bowling ball has a ton of mass, and so the Earth pulls on it a lot more than the Earth pulls on a feather. But that's actually not the reason that bowling balls generally would fall faster than a feather. That more has to do with air resistance, which we'll look at later. Even if they have different masses, and even if they have different forces of gravity pulling on them, it turns out this acceleration, right? The acceleration of gravity near the surface of the Earth, in the absence of air resistance, everything accelerates at 9.8 meters per second squared. So even though the force is different, the Earth does pull more on the bowling ball. They actually accelerate at the same rate. And there's a neat video we can show where the bowling ball and feather fall at exactly the same rate in a vacuum. And of course, on different planets, right? If you go to the moon or Jupiter, then this gravitational field strength changes. So you get different forces than you would on Earth. Okay. Let's look at applied force. Now, this one is a little bit less clearly defined. Gravity, we know exactly. Yeah, it's big objects pulling on something else. Applied force is a little harder to define, perhaps. I basically would define this primarily as a push or a pull from like a person or animal. Notably, gravity is pull only. Gravity doesn't push, it pulls. So we'll go through and just to conceptualize and think about these in the right way. We don't want to view them as, we wouldn't want to think about gravity as a push. It doesn't push. It pulls towards. It's an attractive force pulling towards the Earth or some other big object. Applied force, though, could be a push or pull. And generally, we're going to define that as like from a person slash animal. It also, in parentheses, will say like it could be some mechanical source, like an engine or something like that. The main way I tend to define this, and this is, again, physicists will differ. Not every physicist would say exactly the same, I think, but the way I like to think about applied force is I think of it as a sentient source. If a person, an animal, decides they want to push or pull on something, like a raccoon decides to open your trash can lid and pull on it to get what's inside, right? That's generally how I think of applied force. But that's why I reference an engine or a mechanical source. If a person designed that engine to do some pushing or pulling, you could also lump that in with applied force. We're not going to have to worry too much about that. We're not going to get a bunch of engine problems or anything like that. Mostly this would just be, hey, I've got a person pushing or pulling on an object in my problem. Let's go ahead and call that an applied force. So variable, we're going to use FA. You could use capital A, lowercase a, doesn't matter too much. Units are still newtons. All of our forces are measured in newtons. And the equation, well, it turns out we don't really have one. So applied force is weird. If we think about what goes into, like here, we could say, we can calculate the force of gravity. Well, which planet are we on? Is it Earth? Is it Jupiter? Okay, we've got 9.8 or whatever the acceleration of gravity or the field strength is on Jupiter. We've got the mass. We've got different objects. The Earth pulls more on a car than it does on a bicycle. So we can find that based on the mass of the object and the field strength or gravitational acceleration of the planet we're on. There are things that would go into finding how much force a person uses, but they're kind of weird, like biological things of like, what signals does your brain send? Because your brain knows how hard, roughly, you want to push or pull on something. Do you work out? Like, there's a limit, right? I don't work out a ton, so I can't put out as much force as some bodybuilder who's got insane muscles. And so everyone's got different like muscle mass and the energy from the food they ate and their brain signals sending electrical signals. So there are things like that, right? But that's hard to put into an equation. It's pretty unique to every individual person and every situation. So we're just going to say, hey, this person is pushing with 20 newtons of force, and we're not going to really have an equation to calculate how much force they use based on whatever their body and their brain and their muscles are doing. That's applied force. There it is. We've got normal force. This one is not, people aren't usually familiar with this term. I guess applied force not super commonly thrown around either, but the normal force is, we're going to think of like tables, we're going to think of floors, we're going to think of ramps and walls. So this is a supporting force from a surface. Floor is a surface, a table is a surface, a wall is a surface, a ramp is a surface. Pushing, so this is a push against an object. So the table, the floor, the wall pushes against an object that is pushed or pulled up against it. So we set something on the table. In that case, gravity pulls the object downward, and in doing so, gravity pulls the object up against the table. Or you decide to lean on the wall. Now you are pushed up against the wall, right? You're leaning into it. So whenever you get something pushed or pulled up against that surface, you get the supporting force, which of course, thankfully, prevents us from going straight through the wall, prevents us from falling through the floor, prevents an object from just going straight through the table when you put something on it, right? The solid nature of floors and walls and tables is that you set something on it, or you push against it, or you lean on it to a point. Don't go dancing on the tables, but to a point, and there's enough supporting force to push back and prevent it from breaking or from the object going through. This one is a little weird because the amount of force, and we'll reference this when we talk about equation or how to find it, varies quite a bit. This one actually is very depending on other forces acting. We'll reference this multiple times again when we start looking at like ramps with forces or just some problems that involve normal force and trying to find how much it is. But the basic summary I would say is, if you have an object and you just set your calculator on the table and let it go and let it sit there, gravity pulls down on it. Normal force pushes up and supports it. and that's it. The normal force depends on just gravity. Like however hard gravity pulls downwards, normal force is going to push back upwards to support it. But if you, for whatever reason, take your own hand and push or hit down on your calculator with some additional force from yourself, pushing that calculator down into the table, the normal force from the table, the supporting force pushing back upwards, is actually going to change. It's now different than it was when it was just gravity pulling on your calculator. So, right, depending what forces are acting to push or pull things up against a table or floor or wall or ramp, we get varying forces. All right, this one is variable Fn, and the units are newtons. An equation. So normal force can be a bit tricky in a couple ways. One is we don't really have one, but we'll make a note in parentheses. It is often, not always, but often equal to the force of gravity. Because if you just set something on the table, if you set something on the floor and you place it there, gravity pulls down, trying to accelerate the object or trying to get it to go downwards, right? If you drop something, gravity successfully accelerates it downwards through the air. And the table or floor prevents that object from accelerating downwards by supporting it and pushing back up. And in those scenarios where you just place something on the table or place it on the floor, well, then normal force is just equal to gravity, which is kind of nice because we have an equation for that and we can pretty easily find gravity using its equation. So that's good, but it's not always true, right? Again, if you start pushing on it, in addition to gravity pulling on it, then things get a little interesting. So normal force, we don't want to always equate it with gravity, but there is many situations when the only other force besides normal is just gravity pulling on it, and then we just have the two being equal to each other. There's an important thing here that it's always perpendicular to the surface. So we'll talk more about this, but it's always perpendicular to, so like the surface of the floor or the table, the normal force pushes directly up from it. So that is an important thing. Same thing with a ramp. It acts perpendicular to a ramp, even though the ramp itself is angled. So that'll be a key thing with normal force. All right, tension. This is the force pulling within a taut. So taut just means like pulled tight. Rope, string, or cable. The requirements for tension is the rope, string, or cable does need to be like pulled tight. There needs to be some tautness to it. And then there's a force of tension that pulls within that rope, string, or cable, right? So the tension goes all throughout. Once you pull a cable tight to support a building beam or something, now there's a force of tension throughout that entire cable. So this can do a couple things. In some ways, this can act as a supporting force. Some of you might have a chandelier or fan or something from your ceiling that's like hanging by a cable in your house. I think of like ballrooms with fancy big chandeliers hanging from the ceiling. So this certainly can act as a supporting force, holding up a big old chandelier. Or what can also do is it can actually transfer some force from one end of a rope, string, or cable to another. So we're going to see some objects that are like connected by rope, strings, or cables, even though they're not hanging from the ceiling. So there, it's less of a supporting force. Like if you're hanging something like a picture with a string, you've got that supporting force that's like opposing gravity. But if you connect to things like, hey, here's a box and another box, I'll connect them with a string and then I'll pull them both horizontally across the floor. We're going to look at systems of objects with tension and things later on, and that would be more of the transfer of force. Think of like tug of war as another example. In a tug of war, really it's applied force. The one team is pulling, that's people pulling, applied force. The other team is pulling on the other end, also applied force. And the purpose of the rope is to transfer your applied force to the other team and pull them over to win the tug of war. Now, one key thing to note here for problems and anything involving tension is the amount of tension in a section of rope, string, or cable is the same. It's always the same throughout. I'll draw a real quick example of this over on the side. So if we've got three little objects and we're going to pull them all across the floor and we've got some strings connecting them, we'll do something like this later on. We'll actually do a problem. There's an amount of tension in the left string, and whatever amount that is, 7 newtons of tension, whatever the amount of force is. It's the 7 newtons of tension throughout the entire section of that left string or cable. And then the right one, maybe it's 12 newtons of tension. And that amount of tension, that force of tension, is the same throughout that section of rope or string or cable. So once you have like a length of or a section of rope, string, or cable that's pulled tight, pulled taut, the amount of tension in that section is going to be the same at all points. So you could basically say the tension pulling on the far right block from that rope or string and the tension pulling on the middle block from the right string is going to be the same amount, whatever amount of newtons. And then over here, you've got the tension from this left rope that's pulling on the far left block and pulling on the middle one. That's going to be the same amount of force from that section pulling on both of them. That's an important thing to keep in mind for some stuff in the future, like Atwood's machines. We'll use that. So variable is ft, as we might expect. Units. They'll use some weird stuff from time to time, like sometimes they'll just be like capital T for tension. Like, sure, College Board, do whatever you want, I guess. But our basic variable should be ft. Now, it might seem like at this point, like, do any of these forces have an equation of their own besides gravity? We'll get to them. This one does not. So there's really, we don't have an equation for this. And a big part of that reason is it also, like, if it's supporting like normal force, if it's transferring force, it really depends how much tension there is. Depends, like, how hard are the people pulling at the ends of the rope for the tug of war? Or sure, you could like hang a lamp from the ceiling, but if your kid jumps up and starts swinging from the lamp and there's additional force, now the tension changes and maybe it breaks and falls. Yeah, the amount of tension really depends on other forces that are acting, and we don't have a unique equation for it. There will be ways we'll use Newton's second law to for all these. It's like, well, how can we even solve for them? How can we do a problem with applied force, normal force, tension? Like, we don't have equations for any of these. There will be equations we look at that that we can solve for any type of force, looking at other forces, looking at acceleration when we get into Newton's laws. So there will be ways to deal with this. But we don't have one explicit equation for tension, like this is how you find tension. Next up, we have one that not only has its own equation, two of them, there's two subtypes of this force. This one kind of takes the longest to go through. So this is friction. This is one of the toughest in terms of the amount of things to talk about with friction and the two different types and the equations. There's kind of a lot to do here. But let's start with the basics. This is a resistive or resisting force that opposes object's motion on a rough surface. Yeah, if there's some amount of roughness to a surface, then we'll have some amount of friction. And that's a word to keep your eye out for. If they say an object slides on a rough surface, hey, we're looking at friction. We're going to have to think about you doing stuff with friction. All right, we could think of this as a push or a pull. It really depends how you kind of conceptualize it, how you think about it. So let me draw a quick example. I've got two objects, like here's a box sliding on the floor. So there's your surfaces. The floor could be carpet, the box could be cardboard, who knows what they're made of. If you zoom in really close, even the smoothest surfaces, like cardboard seems pretty smooth. But if you zoom in really close, there's some like roughness and like jagged edges to any surface. So at a really, really close level, the cardboard and carpet have, right, these sort of like roughness, almost like ridges or mountains or like teeth, or they're catching on each other, right? That's the visual I think of. If we zoomed in really close, we'd see like not atoms and molecules level, but some roughness to the surface on a small scale that's like catching and dragging and all that. So if we think about that, it's like, well, are the little rough parts of this pushing on each other, pushing against each other, or are they like sliding across and dragging and pulling on each other as they go? It kind of depends how you like think about it. So I wouldn't worry too much about it. You could pretty well describe friction as a push or a pull, and either one could be just fine. Now there are two types. There are two types of friction, depending on whether an object is moving or not. So if it's in motion, there's one type of friction. If it's stationary and not moving, there's a different type of friction. Yeah, let's get right into those two types. We'll get to the variable. It's probably unsurprising that it'll be F with a lowercase f, force of friction, capital F, subscript lowercase f, but we will specify that in a second because we're going to have a couple different variables, one for each of our types of friction. Static is what we'll start with first. Static, of course, is the word that more means, well, means not moving. If something's static, it's still, it's not moving. So static friction is when an object is not in motion. So this is the force that first of all is going to be matching and resisting any attempts to move an object that is stationary on a rough surface. Now, even, I guess, rough surface, even ice has some friction. We wouldn't call ice rough, generally speaking, but there's some amount of friction on almost every surface. But if something is stationary, like on your floor, on your carpet, or even tile, like tile is smoother, but it has some amount of friction. So let's say your like couch is sitting on your carpet and you want to move it. What happens is there ends up being a range of possible values for this. So in our definition, we'll include there is a range possible values. This is going to come up in our equation for it. We're going to have a bit of a weird looking equation with the maximum possible value described by the right side of the equation that we will look at in a little bit. And the key here is if the forces attempting to move the object, which would be you in the case of moving your couch, exceed the maximum value, then the object moves. Okay, there's a lot there. There's quite a bit. Static friction is quite possibly the most complicated or tricky to kind of get your head fully around out of all of these forces. So we'll take some time to go back through it. I am going to write the variable and equation and whatnot, so we have that written down, and then we'll come back and give some more details. All right, so the variable, now as I said before, the capital F with a subscript lowercase f, that's friction. We're going to add one more subscript s for static. So FFS, capital F, subscript lowercase f, another subscript lowercase s for static friction. So that's our variable. Units are still newtons, and we have an equation. Look at that. We actually have an equation for this force. Now it's a weird looking one because of what we said earlier is there's a range of possible values. So here's what it looks like. It has some absolute value signs in it. We'll talk about those in a second. Force of static friction absolute value is less than or equal to mu. Now the Greek letter, I drew it pretty poorly there, so I'm going to redraw it. The Greek letter mu, it's actually the Greek equivalent of like our letter M. So it's pronounced mu like M for mammal. But I draw it more like a W. Because what it ends up looking like in my mind is like if you have a W, a lowercase w, and you just add a slightly longer tail on the other side of the W, then you've kind of got the Greek letter mu written down. It looks a little different when it's typed. But yeah, it's the Greek letter mu equivalent to M. And we're going to put an S subscript on there. So we'll mention in just a second what that is. We're going to finish the equation though. Absolute value of normal force. So there's a lot to talk about here because normal force shows up. What's that doing in there? What's this mu value? What's going on? Why is there an inequality in my equation? It's nice when things are just equal. How come we got less than or equal to? All right, so let's talk through it. We'll talk about like what each of these are. Specifically, we'll start with mu because that one probably looks the weirdest. Like, what is this doing here? This is called the coefficient of static friction. All right, so what is a coefficient of friction? Well, coefficients of friction are basically how rough or not rough is a surface. We'll look at kinetic, kind of giving away the next type of friction. We'll look at like sliding or moving objects. But what a coefficient of friction is one thing we could notice about all these values, with the exception of a few of them, is they're decimals, right? They're somewhere between like 0 and 1. So iron on iron. So this is like material combinations. And as you might guess, there's infinite combinations. You could have aluminum sliding on aluminum or stationary if it's sitting there and you're trying to move something. You could have brick on wood, brass on ice. So all these are combinations of surfaces, and you could have different conditions, whether it's dry or greasy or whatever. But yeah, the coefficient of friction basically tells you if it's a high number, if it's a big number, there's a lot of friction. Well, here's a low one that's pretty obvious. Ice on ice. We tend to have a low friction on ice, so there's very low, both of the coefficients, so static and kinetic friction, they're very low. So very small amount of friction versus something like, okay, here's a good one. Rubber and asphalt. I'm really glad we found this one because rubber and asphalt is your car tires, right? There's a reason we use rubber because there's a lot of friction. 0.9, like the biggest ones, again, some of them for whatever reason go above 1. There's some weird math there, but for the most part, they're between 0 and 1. So 0.9 is really high. That's a big amount of friction. We want friction between car tires and the road. You do not want to be losing friction and slipping and sliding all over the place, right? So friction is good. We want friction with rubber and asphalt. So it's a high value. If you do start slipping and moving, there's like kinetic friction involved, and there's a learning moment here, right? They told you to drive slower in the rain. Well, guess why? Because dry asphalt, I guess they only have the kinetic for whatever reason, but dry asphalt has a higher, this is like 0.5 to 0.8, versus wet asphalt is lower, 0.25 to 0.75. So you get less friction between your tires and the road when you're on wet asphalt, which most of you probably knew anyways. You're like, oh yeah, they told me not to drive in the rain because you could slip around, but right, the physics is there. It shows that coefficient of friction is much higher. We get more friction on between rubber and asphalt in general, and especially when it's dry. All right, but yeah, that's coefficient of friction is like we've got lots of you don't need to memorize these. It's just combinations of materials. What is sliding on what? What's the contact between the two surfaces that could slide? Or in static friction, in the case of static friction, they're not sliding yet. They're stationary, and you're trying to move something. You're trying to slide it while it's stationary on that surface. So depending on the combination of the two surfaces we're looking at, we get varying or different coefficients of friction. Again, it's basically just saying how much or little friction is there relatively speaking on this surface. Ice, you're going to get low coefficients of friction, small amount of friction. Rubber and asphalt, large coefficients, lots of friction. Okay, so that's your coefficient of friction. Normal force. Again, we'll do hopefully a lab activity that kind of gets at this a little bit as well and gets you a hands-on experience with why does normal force matter, but I'll kind of try to draw this out a little bit as well. So if you're trying to move something, so let's say you're trying to move that couch that you're sliding across the floor and you push on it. So you push like to the side. Static friction is going to try to prevent you from moving it. It's going to try to match and resist your attempts to move the object. So if you push with 10 newtons of force, the two things that determine what goes on with the friction in the friction equation is number one, what's the coefficient of friction between the carpet and the couch? How much friction is there in general between those surfaces? So the surfaces matter, right? So we could say of this coefficient, this is really dependent on the surfaces. What is the material? So that's the first thing, right? What are the materials making up the surfaces? How much friction is there between your couch and the floor? The next is normal force because there's a force of gravity pulling down on the couch and there's a normal force from the floor pushing back up. And because of that, we might think, well, so then is it just gravity? Like, is it just how hard it pulls down into the floor that makes it like easier or harder to push or pull it? Well, sort of, but it's not just gravity. It's not just how hard it pulls down. It's actually the normal force as well. And when we look further at normal force, we'll do more details on like, hopefully I'm hoping to use some in-class time to dedicate to like normal force that changes and how that affects friction, the lab on friction with testing some of your force sensors and measuring with those, looks at normal force and friction. So the basic summary is what would make it harder, what would make there be more friction is not only replacing your carpet with Velcro, which has a ton of friction, or something really rough like sandpaper, trying to slide your couch on sandpaper or something like that. So the materials matter, but also if your sibling comes along and plops themselves on the couch, or your friend comes in and decides they're going to sit on the couch right when you're trying to move it, that's very unhelpful. Because what they're doing is they're adding additional downward force onto the couch. The floor, in response, is supporting, pushing upwards with a normal force. and it's supporting with more force because your friend sat on the couch. And now it becomes harder for you to move because there's this normal force gets bigger, and the whole right side of this equation is going to get bigger. So the idea is that based on the materials and the surface, how big is the coefficient of friction, the mu value, and then how much normal force is there? Which again depends, is someone being really annoying and like pushing down on the thing while you're trying to move it? Maybe your friend comes in and is like, "Hey, I'll help out." And they like lift up a little bit. They pull upwards on the couch. That would actually help you a bit because now they are providing an upward support force to help out the normal force, and the floor doesn't need to push up as hard on it, so there's not going to be as much friction. To visualize a little bit, the sort of like jagged edges I mentioned before, if you really push down on it or your friend jumps on the couch or sits on it, what happens is you're like pushing those together. You're like squishing those jagged edges into each other, and you're making even more, when you try to slide it, there's even more edges catching and dragging on each other and preventing it from moving. So you get even more friction. But yeah, so this equation tells us that depending on the materials we're using and depending on the normal force from the floor or surface pushing upwards or pushing onto the object, this could also apply to a wall where the normal force isn't pushing upwards, but there's still a normal force from the surface. You multiply those together, the mu value, which again is going to be usually between 0 and 1, like 0.6 or 0.7 or 0.3, times whatever your amount of normal force is. So this right side of the equation is this. That is the maximum value. So that maximum possible force of friction is mu times normal force. That's why there's an inequality. Because let's say you solve this and you say, all right, the mu value is 0.5. That was given to me in a problem. You don't have to memorize it. You don't have to know it or whatever, right? They're like, you're sliding something on the floor and the coefficient of friction happens to be 0.5. And the normal force in that scenario is 100 newtons. Okay, so 0.5 times 100, and then you get 50, right? So what that tells you, if your right side, the circle in blue part, if that is 50 newtons, it means the maximum possible force of friction is 50. So if you push on that couch with less than 50 newtons, so you're being lazy or you just don't want to push that hard and you only push with 30 newtons of force. Well, this equation would tell us if the force of static friction can be less than or equal to 50, your 30 newtons is not enough to move it. Not only that, but the couch will exactly match your attempt to move the object. So just because you solve this is the tricky part about static friction. It is the toughest of all these equations. Just because you solve this doesn't mean that, oh, I found 50. It's 50. So yeah, that's just my friction no matter what. The friction depends on how hard you're trying to move it. So it will match your force. If you push with 10 newtons, it'll push back with 10 in the opposite direction. If you push with 30, it'll push back with 30 newtons in the opposite direction, or pull, depending how you think about friction. So friction matches your attempts to move the object up to the maximum value. If you push with 55 newtons of force or even 51 newtons of force and the maximum was 50, you have successfully moved the object because you pushed on it or pulled on it harder than the force of static friction was able to resist. So that's what the inequality is. The force of static friction could be anything less than or equal to whatever this maximum value is. So doing the equation, what it really just does is it tells you what's the biggest that static friction could be here. And once you find that, again, they're like, okay, so it's 50 newtons. So in order to move the object, we have to push or pull with a total force bigger than 50 newtons in order to exceed the maximum static friction to get it moving, so that static friction is not able to match our force and keep the object stationary. Because if you don't push hard enough, it's not going to move. The other really neat thing and kind of fun thing here is it's very good for us in the real world that this is an inequality. Because if you think about something like a freight train, there's a lot of mass on a big old train. And the normal force, which if the train is just resting on the tracks, the normal force is just equal to gravity, but that's a lot of gravity. We're talking thousands, like tens of thousands of newtons of gravity. So if this normal force is huge, there's some coefficient of friction between the train and the tracks, the iron material or whatever. So it doesn't really matter what that is. If you have 300,000 newtons times 0.5, you've got a huge possible amount of force, which means you would have to get a lot of people to push on that train to get it to move, right? Or the train engine is outputting a ton of force, like a lot of force to get it to move. It's very good for us that it's in fact an inequality and not an equals sign. Because if it was an equals sign, that would mean you come up and you touch the train even a little bit, push on it with 1 Newton of force. If it were to push back, if it were to resist your attempt to move it with the full maximum value, you would go touch a train and get like blasted into outer space or something. Maybe not quite that far, but you'd get severely injured or killed by touching a train. So it's good that physics works like if you put a Newton of force, 1 Newton, onto a train, and the static friction resisting will just be 1 Newton. It will just match your force. It's not immediately going to the maximum value. Anyways, that's a kind of a weird side thing, but it's kind of fun, I think. So, summarize. Static friction is a tricky one. When an object is stationary on a rough surface, any force or forces trying to move it will get matched by the force of static friction, provided that static friction is able to match them. So you got to check with the equation, say, all right, we plug into the equation, what's the mu value, what's the normal force? Okay, I found this right side here. I found the maximum force of friction is, 50 newtons, which means any attempt to move it that is 50 newtons or less does not succeed. We don't move the object. Static friction matches our force. It stays stationary. If you exceed that maximum value, which is found by the right side of the equation, then it will move. And that's the inequality, right? Static friction depends on it will be anything less than or equal to that maximum, and it depends on how hard you're trying to move the object. It will just match your force. That's static friction. That's objects sitting still, trying to get them to move. Let's do kinetic. This one is much more simple. We already are familiar somewhat with the word kinetic or kinematics, right? Moving, motion. So kinetic friction, unsurprisingly, is for moving objects. This is the force resisting the motion of an object that is moving on a rough surface. So unlike static friction, this does not have a range of possible values. It is simply equal to the amount in the equation. It's much more simple. So it doesn't have the inequality, the range of like, well, it could be something less than 50 newtons or something less than 100 newtons. It just depends how hard you push or pull because it's matching your force. Kinetic friction is much more simple. It's like, well, if your object's moving and it's sliding on a rough surface, you have some kinetic friction, and the amount is much easier to find. So our variable is the force of friction kinetic. So that's going to be capital F, subscript lowercase f, subscript k, force of kinetic friction. Units are newtons, of course, and we have an equation for it. Absolute values are going to show up in here. So we're going to get absolute value of the force of friction kinetic equals. There's that mu value again. But instead of the coefficient of static friction, it's the same thing in that table of values where we saw ice on, wood on ice and rubber on asphalt and aluminum on aluminum and all the possible combinations of materials. There's one value for static friction. How much friction could there be if it's sitting still? And there's another value for kinetic. The reason they're different is, and we can pop back over to that table just briefly, you generally are going to see, and we can observe this here, more friction from static than kinetic. The basic idea being it's harder to get something moving. You're going to have to put more force into getting it moving to overcome the static friction. But once it's moving, there will generally be less friction overall. So the static tends to be bigger than the kinetic. Yeah, it's like, well, it's harder to get it going, to get it moving against static friction. Once it's moving, then this kinetic is going to be smaller. So it's summarizing the idea that it's generally easier to keep something moving. There's not quite as much friction as when you're trying to first get it going and overcome static friction to get it moving. All right, and then lastly, we have, once again, a returning visit from normal force. Okay, so To summarize kinetic friction, if something is moving or sliding on a surface that is rough, then kinetic friction is the force resisting the motion. So if your velocity is like, hey, the object slides to the right, it's sliding to the right across the floor, that's its velocity direction that it's going, um, then kinetic friction acts to the left in the opposite direction, right? Opposing, resisting that direction of the motion of the object. And the equation to find, and we can talk more about absolute values, but basically part of it has to do with like normal force from the floor. If it's sliding on the floor, normal force from the floor would be upwards, whereas friction would be like to the left or to the right along the floor. So we don't want to give the idea that the direction of normal force is the exact same as the direction of friction, because it's not. In fact, they're actually perpendicular to each other, which is kind of weird. So this equation does not help us find direction. It only gives the magnitude of the force of kinetic friction, or in this case, the magnitude, right, absolute value of the maximum possible force of static friction. Luckily for us, the direction of friction is really easy to find because you just look at like what direction is it sliding? If it slides to the right, friction is to the left. Static friction, not too hard either. If you try to push it to the right, it pushes back to the left, resisting your attempt to move it. So that's easy enough. But yeah, this equation tells us, depending on the mu value again, the materials of the surfaces, what is sliding on what materials are they made of, which you will not have to get into the weeds with types of material, but they'll provide you those coefficients as you need them, or you might solve for them, right? If you know normal force and you find friction, then you could isolate and solve for mu as well. But yeah, depending on the materials, what is sliding on what are these surfaces made of, also depending on that normal force from the surface supporting and pushing against the object that is sliding directly. But yeah, depending on that normal force, which acts perpendicular to the surface, pushing directly up from the floor or the table to support the object, or pushing directly out and away from a wall if the wall is supporting an object. Depending what that normal force is, and depending what the materials are, then we can look at how much friction is resisting that motion to try and slow it down, because that's, of course, what friction does. It slows down and stops objects that are sliding, and it tries to prevent us from moving objects that are stationary on a rough surface. Well, we're going to call it there because I don't want the video to get terribly long, and I ran out of room for my notes. There are two more types of forces that we'll address in the next video, along with, I think, looking at some things with Newton's laws of motion. Thanks for watching. We'll see you all in class and for the next video. Have a good one.